Hi, everyone. So welcome to the test seminar. Today, we are very pleased to have Professor Cristiana stand from George Mason University to visit us. Cristiana is currently a professor and associate chair in the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University. She received her bachelor's in physics and master's in atmospheric physics from University of Bucharest. And then she got her PhD in atmospheric sciences at Colorado State University. After that, she moved to COLA, the Center of Ocean, Land, Atmosphere, and then joined the faculty of George Mason University, and still stay part of COLA, I guess. Cristiana, apart from her research, she's also very engaged in national and international scientific leadership. She's serving as vice chair of the World Climate Research Program's Joint Scientific Committee, and she also serves as LOAA's Unified Modeling System S2S and Medium Range Application co-chair. So yeah, welcome. And
thank you very much, Edmund, for the introduction and for the invitation to visit Stony Brook. It's great to be here back. And it's been quite some time since I was here, but during that time, I had the privilege to collaborate with many of you faculty and postdocs and students. So today, I will talk about some research that is mostly done in my spare time. So it's not so well probably known, but I hope you will find it interesting, and I hope you will be stimulating for the graduate students who are still deciding on the topics for the research projects. So the title of my presentation is the subseasonal and seasonal variability of the Northern Hemisphere mid-latitudes. It was working earlier, but it's not working now. Okay. So in my talk, I will cover why I became interested in this topic, and then I will provide some technical description of the analysis methods that I've been using. Then, obviously, I will describe the mid-latitude oscillatory modes, and then talk about their relationship to the surface weather, their relationship to some of the tropical variability, and then cover a little bit of their potential predictability, and then finally wrap up with some conclusions. So here we are in this slide, we are looking at the zonal wave number frequency power spectrum. And for those of you who are familiar with this kind of analysis, which is typically done for investigating the variability in the tropics, you probably are thinking, well, why this look different from what I am expecting? And the reason why they are different, it's because they have been constructed using the 500 hectopascal geopotential height daily anomalies between the 30 and 70 degrees north, so in the northern hemisphere. So when I constructed these diagrams, the thing that struck me the most was the fact that there is a lot of power in the subseasonal to seasonal timescales, which is shown here by these dashed lines. So here we have the line of 45 days, and this one is the 120 days. And this power is seen both during the winter and summer. The second thing that it was interesting was the fact that this power shows some asymmetry between the westward propagating regions, which corresponds to these negative values on the x-axis, and the eastward propagating region, which corresponds to these positive values of the x-axis. So this asymmetry suggests that these powers correspond to some propagating oscillatory modes. So this was the motivation why we would like to find out more about these propagating modes. But then the question is how to extract these oscillations. So we saw them, but what can we do to find them? Well, we have some tools that we could use. So we can do an EOF analysis and then calculate the power spectrum associated of the principal components to identify some periodicity, and then find the pairs with similar periodicity, and with those pairs we will be able to identify the oscillations. We can also apply some autocorrelation, which is a known tool for identifying extracting some signal that is buried under noise, or identifying some fundamental periodicities in signals. Or we can combine the EOF analysis with the autocorrelation methods, and that is being done in the so-called multi-channel single spectral analysis, or MSSA. So this is what we did. We applied the MSSA, and since this is not a very well-known method, I will take a couple of slides to explain to you what do we mean when we say that we apply the MSSA analysis. So for that, let's consider a 2D data matrix, which is shown here. And let's assume, for the sake of simplicity, that we have a single variable that is defined at m locations, and we have m different times for that measurement. And we can also write this in a compact form, which is shown here. Then in order to apply the MSSA analysis, we will construct the time lag version of each of these elements here, x, with L lag copies of itself, where this L should be obviously smaller than M. So when we do that, this is how the lag time version of each of these elements looks like. So we obtain this matrix that has L columns, and then we'll have these M prime rows, where M prime is M minus L plus 1. And then when we put all of this together for every point for which we have observations, we construct the so-called multi-channel trajectory matrix. So next, we will calculate the covariance, we call it lag covariance matrix of this x hat, which is shown here. And in each element here is actually a block, and this block is the covariance between independent channels. So each of these blocks, it is scaled by this M prime, and remember that M prime is related to this L, to the lag. So this lag represents the key parameter that determines the temporal scales that are captured by our analysis. So if we are interested in isolating a signal that has, let's say, 50 days, then we would need that this L to be at least 50 days, or even longer if we want our signal to be better described. So now, just to summarize, what is the conceptual difference between EOF and MSSA? And I'm using this schematic from a paper by Kim et al., in which let's consider that at the random location, we have a system response to a random physical process that looks like this time series here. So when we do an EOF analysis, right, then we decompose this signal into a constant component, which is the eigenfunction. So this can be interpreted as the characteristic physical response. And then also the principal component that retains the temporal variation of the signal. And this can be interpreted as some stochastic undulation. Now, when we apply the MSSA to the same time series, these physical characteristics also retains a temporal structure. So the eigenfunctions are not constant in time, are not, yes, they include temporal variability. And also we have the principal component, which is a time series, and it's smoother than in the case of the EOF analysis. So basically, if we want to further summarize this, we can say that the EOF analysis treats each time point independently, whereas the MSSA analysis incorporates a temporal structure by embedding the data in a time-delayed coordinate system. So this is the difference between the two methods, and I'm sure all of you in this room are familiar with EOF. So now let's see what happens when we apply this MSSA analysis to 500 millibar geopotential height in the northern hemisphere between 30 and 70 north. So we obtain 3 modes, so are 3 pairs of the so-called reconstructive components. And one pair has a period of about 120 days, and we refer to this one as the mid-latitude seasonal oscillation, or MLSO. Then we have another mode, propagating mode, because we have these pairs that have the same period, and which here is 45 days, and we refer to this one as the mid-latitude intraseasonal oscillation 1, or MLISO 1. And then we have a third one, which has a period of about 28 days, and we name this MLISO 2. We are actually not the first one who did this kind of analysis. This has been done before, like in 1993, Law and Votard. They did not conduct the MSSA analysis over a global region. They looked at some limited domains, and they did find a period which is an oscillation with a period very close to ours, but they discarded because they said, well, this is just the third harmonic of the annual cycle, so it's nothing interesting to pay attention to. Then they identified an oscillation with a period of about 70 days, and they associated this with some fluctuations of the Atlantic jet. Another oscillation with a period similar to our MLISO 1, which they identified only over the Pacific sector, and another one closer to ours, and they said, well, this is just the harmonic of the 70 days, so it's not worth paying attention. And then Gill and Moe, even earlier, they applied just the simple, not the multi-channel, so used only some time series, and they identified additional oscillations, one with the 48-day period and another oscillation with 23-day, and these were global modes. So let's look here at their patterns of these oscillations, and MLSO is shown here, the pattern, and then MLISO1 and MLISO2. So here it's easy to see that these are global patterns, but they also have some with regional centers of action. So in MLSO, we see this elongated North Atlantic dipole that has anomalies over Eurasia and also over the North Pacific. In MLISO1, we see some centers over the North Pacific, North Atlantic, and they have this particular orientation in the northwest and southeast direction. And then MLISO2, it appears as a tripole pattern that has the centers with the same signs over the Northern Europe and Eastern Canada, and opposite sign over the Alaska. So figures here on the bottom show the standard deviation of each of these oscillatory modes divided by the total daily variance. So if we combine them, we see that all three of them explain about 30% of the daily variability in the mid-latitudes, and centers where we see action here in their patterns are also regions where they have the largest variability. So I mentioned to you that they are propagating modes. So here in this slide, we are looking at some of the propagating characteristics, and the MSSA analysis allow us to calculate the phases of each of the oscillations. So each column shows the phase 1, 2, and 4 for each of the oscillations, and the other 4 look about the same, but the signs of the anomalies are reversed. So these diagrams and also additional analysis that we did, I don't have time to show you here, indicate that, for example, MLSO propagates with westward with a phase speed of about 3-4 meters per second, westward of 120 west in the mid-latitudes, and in higher latitudes appears as a standing oscillation. It's just going up and down. And also, it displays some northward propagation over the North America and North Atlantic. MLISO1 also propagates at the speed of 10-12 meters per second in mid-latitudes and slower in high latitudes, and it doesn't show any propagation characteristics in the north-south direction. And MLSO2 propagates faster at 20 meters per second in high latitudes, and it's a standing oscillation in the mid-latitudes. And it does show some northward propagation over the North Atlantic, and it's a standing oscillation over the North America. So now moving into the relationship between these modes and the surface weather. So there are clear relationships between the phases of these oscillations, which are given in each of these panels, and 2-meter temperature anomalies shown in shading. And I will only emphasize some relationships with CONUS. So, for example, we see in phase 1 for the MLSO above average temperatures over the western United States and below average temperature over the eastern United States and also Canada. In phase 2, we see below average temperatures over the western and central United States, and we see these regions of positive anomalies over the eastern and southeastern United States. In phases 3 and 4, we see that US in phase 3 start to develop these warm anomalies, and they get more amplified in phase 4. Similarly, there are some relationships to the 45-day oscillations, like we see above average temperatures across central US, and these below average temperatures over the northeastern coast of North America. We see this almost the entire southern US is covered by negative temperatures in phase 2 and positive temperatures in US and North America. And we see above average temperatures over the northwestern and North America and central US in phase 3. And this switch to this negative temperature anomalies on the west coast and east coast. There is also some seasonal dependence on how the temperature varies. So in this study, we instead of looking at each phase, we took the time series associated with MLSO, and we separated the values in terciles. So the red part here represents the upper tercile, and we refer to this as above normal MLSO conditions. The blue ones represent the bottom terciles, and we refer to this as below normal MLSO conditions, and values in the middle are referred as the normal MLSO conditions. So we construct composites of 2-meter temperature over the United States for an extended winter period and an extended summer period. And we see here that during winter, in these above normal conditions, almost the entire US is covered by negative anomalies in surface air temperature, and they become positive during below normal conditions, and maybe a little bit of negative values during normal conditions. During summer, we see that the signs persist, negative values here, but the magnitudes are much smaller than during winter. We did the same analysis for precipitation, but unfortunately, we did find some relationships in terms of the patterns, but the statistical significance test that we applied here in this study did not show significance. Using other tests, we were able to show some significance, but here we had a very restrictive statistical significance test applied. So probably some of you have already asking yourself, well, some of these patterns look very similar to some canonical patterns like NAO, PNA. What about there is any relationship between these modes and the canonical modes? So when I first started looking into this, I thought, wow, this will be actually related to this canonical mode, so it will be so easy for me to advance these ideas. Well, it turns out that no matter how much I tried, I was not able to find a relationship between them. So here I am only giving you one result. So what we did, we calculated, we took the time series of PNA, NAO, and including NINO 3.4 ENSO. And the same way that we separated the time series of MLSO into terciles, we did the same thing with the PNA index, with the NAO index, and with NINO 3.4. And the panels, each panel here, the one that says above normal and below, corresponds to above normal PNA conditions or NAO conditions or NINO or ENSO conditions, normal and below. And the bars in each of these panels represents MLSO. If it's blue is below normal, green is normal, and red is above normal. And we did this for both winter and summer. So the idea here is that if we see that, for example, if we look at a normal condition, so the canonical modes are in normal conditions, if MLSO is it's just masquerading, let's say, one of these modes, then we will also see that mode being in the same normal conditions, and the same with the others. But it doesn't turn out to be the case. So, for example, in winter, if we just refer to winter, when PNA, NAO, and ENSO are in normal conditions, they are associated with above or below normal MLSO conditions. If we look, for example, at the above normal conditions, so all the canonical modes are in above normal conditions, they seem to be mostly associated with normal or below normal MLSO conditions. And the same thing applies to below normal conditions. So they are not, so there is a difference between these mid-latitudes oscillations and the other canonical modes of variability in the mid-latitudes. So now let's move on and look at the relationship between, I only looked at MLSO relationship to the tropical variability. So this is what I will present here. So in these panels, I am showing the OLR anomalies composited for the 8 MLSO phases. So if we pay close attention, we see that in these phases 4 through 6, we see some convective activity that being OLR, the convective activity for the students here, it's the one associated with negative values. So we do see some convective activity propagating from the Indian Ocean across the maritime continent, which looks similar to the propagation of convective activity associated with the MJO. But there are also some differences between the MJO propagation and this convective activity. So, for example, we know that the MJO propagates mostly eastward and slightly southward, but the convective activity associated with MLSO tends to propagate more northward than southward. Another interesting thing we notice here is this long stretch of convective activity that looks very similar to an atmospheric river structure that extends from the warm pool across the Hawaii and reaches the west coast of United States. there is also some significant convective activity over the South Atlantic convergence zone here. And this region of convective activities has been documented as being relevant to the tropical cyclone activity in the Atlantic. So that's the story about MLSO. What about MLISO1? So for this one, because the period of the oscillation, it is so close to the MJO, initially I thought that it will be, when I look at this kind of composites, I will be able to see something very similar to the MJO propagation. But surprisingly, it was looking at these composites, it's very hard to say that this looks similar to the MJO propagation. So not convinced that that's the case. And these composites are actually done at lag 0, but we can look at different lags because it will take some time for the MJO in the tropics to reach the extra-tropics. But it doesn't matter what lag we are looking at, the picture does not change. So then what I did, I took these patterns, the time series of that were used to construct these composites, and I did an EOF. I filtered the daily OLR anomalies to retain the variability in the 20 to 100 days. And then I did an EOF analysis using 5 days prior to the to each MLISO one phase. So this is what is shown here, the EOF1 for each of these composites, and for each phase. So only EOF1 it is shown here, and all of them, for all phases, the variance explained by this EOF seems to be consistent. It is small, but remember that this is daily variability, so we cannot expect very large variance explained. And in this case, we do see some of the patterns resemble the MJO propagation that we are familiar with. So with that in mind, I said, well, there must be something, but we need to find a way to be able to identify that. So next, what I did, I took the for each of the MLISO1 phases, which are here 1 through 8, I calculated the MJO phases, which are shown by these lines or the numbers shown here. And I took the ratio between the number of days in each MJO phases and the number of days in the MLISO1 phase. Right? So the idea here being that if there is an overlap between some of these phases, then we can interpret the MJO as being the forcing of that particular MLISO phase. So here in these highlighted phases, so we can see that, for example, in MLISO phase 3 and 4, the MJO seems to have more preference in being in phases 7 and 8, and the opposite when the MLSO is in phase 6 and 7. MJO seems to prefer phases 3 and 4, and this can be seen even better if we subtract from these values the climatology of the MLISO, right? So exactly the same. We count the days, but we subtract the MLISO presence. So now we can see that in phase 3 of mid-latitude oscillation, MJO has this preference in phases 7 and 8, and in MLISO phase 6, MJO likes to be in phases 3 and 4. So I think this is an interesting result. I don't have more about this. I am very interested in finding more, but that's all I have for now about this. So now let's move on in looking at the potential predictability of these oscillations for the surface weather over globally. Yeah, here I have only results for the global domain. So in order to understand whether or not, I mean, obviously, if they are related to surface weather and they have periods longer than weather events, they can represent a source of predictability for the weather events. But if models can actually have skill in predicting these modes on their own, then that potential predictability can be extended even better. So first, let's look at the anomaly correlation for the time series of MLSO. So it's not dependent on any phase, it's just the whole time series. For the winter season, which is DJF here, and summer, JJA, and we looked at 4 models from the S2S database. And for those of you who are not familiar with the models, BOM is the Australian model, UKMO, it's the model from the UK Met Office, CMA is the model from China Meteorological Agency, and ECMWF probably doesn't need to remind you what model is this one. And the solid line represents the anomaly correlation, and the dashed line represents the persistence for each of these models. So we see that during winter, all models beat persistence. So that's a good sign. That's not actually the case for the summer months. So even though the oscillatory modes, they persist or have a period of 100 days regardless of winter and summer. So this is telling us that this persistence in the modes does not necessarily translate into forecast skill. So on the right here, I am looking just at the anomaly correlation for these are weekly anomaly correlations for each models, and month by month I am showing here. So we do see that, for example, during winter, there is this high correlation across the 4 weeks. But again, during the summer, the values of the anomaly correlation, it is lower. But so this analysis is telling us that MLSO defines a flow regime with higher predictability. So there is hope that looking at forecasts that have, for example, MLSO in the initial conditions, that will increase the predictability in the mid-latitudes. And we tested that by looking at the by applying the analysis to the T2M forecast scale. So here I am showing just the anomaly correlation in the T2M anomalies average over this domain that we are working on, 30 and 75 in the 4 models for January and February. So we see that, for example, in winter months, the scale, it is higher in the first 2 weeks, but it drops in weeks 3 and 4. And that's consistent across models, and it becomes and this happens mostly during winter. So, and we see some difference between in the scale between November, December, and January than February, March, and April. So to test my hypothesis that having MLSO in the initial conditions of the forecast, and not only MLSO, but being interested in what phases of the MLSO actually favor or the influence the 2-meter temperature anomalies, I am looking here at the forecast scale. Each panel corresponds to one of the models as a function of the MLSO phases, where I have a 0 here. So that means that MLSO, it's not in any, or is in a neutral state, that it doesn't belong to any phase. And then on the vertical, I have from week 1 to week 4. So we see that, for example, for some models, not all of them, for example, for the UK Met Office, the anomaly correlation in week 5 gets extended to all the way to week 4 when MLSO is in phases 5 and 6. And the same thing, there are some also during February, March, and April, there are some phases that favor the that provide more potential predictability for the 2-meter temperature in the extra-tropics. But this is not consistent across all models. So I think with this, I will wrap up here and say that in this study, we show that on subseasonal to seasonal timescales, the atmospheric variability of the mid-latitudes is dominated by 3 oscillatory modes. And I am showing you again here the patterns, but in addition to the patterns, I am also showing their time series. And as I shown you in the schematic diagrams, looking at the difference between the EOF and MSSA, we see that their time series look smoother than the time series that we are seeing when we look at the principal components from the UFS analysis. These modes propagates westward around the globe and also they have some small meridional propagation. And the empirical evidence that I show here suggests that these modes could be linked to tropical variability. They also show a significant impact on the large-scale circulation. So, for example, during winter, normal MLSO conditions, above normal MLSO conditions can cause below average surface temperature across the United States. And for example, during summer, below normal MLSO conditions can cause strong above average surface temperature across the US. And we also show that MLSO has an impact on the forecast scale on the hemispheric 2-meter temperature. And the impact seems to be stronger during the extended boreal winter. And we know that this is the time when the deterministic probability in the extra-tropics is limited by the dynamical instabilities from the mid-latitude weather. So this can provide additional scale during that time. And the phase of the MJO with the strongest impact, the MLSO with the strongest impact seems to not be consistent across the models. And this might suggest that projection of large-scale circulation on the surface weather might be deficient in some of the models. So I think that's all I have. Thank you very much for your attention.
Okay, great. Thank you.
Happy to answer questions.
Yeah, so let's have some questions. Yeah, Barat.
We're in this Mid-Latitudes also. I was curious, like, what's the physical mechanism? Are they just the internal actual modes of like oscillation, or they just land ocean contrast thing? Because like MGO is an internal phenomenon, because you can simulate MGO on aquaplanets on a symmetric, but no variable, like uniform SST, like. Is it
not quite uniform? You do need to have a meridional distribution.
No, you can get it like people simulated completely constant SST on the whole planet. You get adjusted. Can you get those things on aquaplanet?
I did not try. I mean, regarding the questions, what are their physical mechanism driving this? I really want to find out these questions. But as I said, this is something that I've been doing when I have time. So that's a very good question, and I do want to find out. But at this moment, I don't have any modeling results. I don't even know if global models are actually simulating these modes, and it was easy for me to look at these forecast models because I'm using them for other projects. But
also clarification question. I'm not the expert on all those forecasting things, but when I look at your previous figure,
this
this one. Why, when your lead time is 0, your pattern correlation is 0.75?
Because it's not straightforward to extract them from the forecast. It's like, so you need to do, so they are extracted by doing projections of these patterns. I cannot do MSSA analysis because in the end, so to extract, this is a detail that I think I forgot to mention. We use 241 lags to be able to extract an oscillation with a period of 120 days. You need a lot of lags, and this forecast have 45 days. So I do a lot of massaging of the data to be able to reconstruct these modes in the model. So I don't apply MSSA to the model data. Now I can do that in climate models, but not with the forecast models.
So Yeah, I just want to another clarification question. So, if I understand you correctly, the upper curve is the economic correlation predicted by the model, and the dash curve is the persistence.
Yeah.
So actually, even in summer, it seems that the models are doing better than persistence. So I don't see why you said persistence. Yeah, not all of them, but it's about the same though. Even none of them is beaten by persistence, or just a little bit.
A little bit, yeah. To me, this doesn't look good.
Uh-huh.
I would not consider this a good model. This
Uh-huh.
one, yes, but not this one.
Mm-hmm.
Or
Yeah.
yeah.
Any other question? So I have another question. So you were suggesting that there's some relationship with MJO. So when you attract the UF out. So have you looked at how whether this mode, the MLS ISO 1 mode, the teleconnections actually resemble some of the teleconnections that we sort of got from MJO composites?
So yes, so for example, I mean the MJO teleconnections could be the NAO or PNA, right? Are you asking about the canonical modes?
No, I mean because the correlation with MJO,
Yeah.
this correlation with MJO, and MJO actually there are composites of the MJO wave train that it excites. So each phase of MJO correspond. People do 0 LED, 10-day, 5 days LED, 10-day LED composites of the mid-latitude.
Oh, yeah,
It's anomaly. Yeah, and is there any? Did you compare with those and see whether it actually resembles some of those waves that are supposedly excited by the MJO?
So phase by phase with the MJO, the composites of phase by phase with the MJO, I did not look at them, but I do have yeah. So my thinking was that, you know, so for example here I have, for example, the this one is MLISO1 composites for each phase, right? And the geopotential, this is the geopotential height, right? So to me, all of them, I mean, look like PNA, right? Over United States. But then when I calculated the correlation between the PNA and each of these composites, only in these phases, the phase 2, I got a high correlation between the MLSO and the PNA, right? But very, very low correlation for the other phases. So this is suggesting to me that at some point they project on each other, but they are not exactly the same thing, since this relationship is not consistent across all phases. But that's a good idea. Yeah, I could look at the composites of geopotential height for each of the MJO phases, and then phases of MLISO1. Yeah, I have not done directly that one. Yeah, that's a good suggestion.
So are there any questions from?
There is a question there. Oh,
Hi. Could you go back to your third to last slide? Yeah, that one.
Yeah.
It's not my expertise, but it looks fascinating. I see a lot of high frequency stuff in some years and very little high frequency stuff in other years. Is that accurate observation or interpretation on my part?
yeah, that is, yes. There
So-
are years when the amplitude is, I will not, I mean, the frequency is the same. The amplitude is
Yeah,
different.
but
The amplitude,
if I,
yeah,
looking at that third one,
yeah,
there's a lot of high frequency stuff in 1980, 1979, something like that. A little bit, I can't quite read the numbers. And then there's very little high frequency stuff 6 months later, something like that. How is that manifested in some way in observations?
this is based on observations,
Yeah,
yeah.
but if I'm sitting someplace, do I see a lot of high frequency stuff at one time and very little high frequency stuff another time?
Yeah.
Okay.
Okay, yeah, thank you. So I think we can move over to lunch and then we can continue the discussion. Unfortunately, our speaker has to leave shortly after lunch, so we won't have meeting with the student after lunch. So
Before we part, I have one more thing that I wanna advertise here. I'm taking this this time. So I do look for a postdoc researcher to work on a project that's not related to this one, but it is to evaluate the biases and skill in the S2S forecast generated with the NOAA-UFS model, and in particular for evaluating the ability of UFS to predict extreme events and more precisely precipitation. So we have done a lot of analysis looking at the impact of large-scale drivers, but now I plan to look at more regional or local drivers in assessing these errors in extreme precipitation. So if any of you is planning to graduate this spring semester and are interested in working on this project, feel free and reach out to me. Thank you.